Properties of probabilities. Suppose S is a sample space for an experiment, and let A, B, A1, A2, and so on be events defined on S. A probability will always lie in the interval of real numbers between 0 and 1. This is because the probability of A is the sum over all points little a in A of the probability of these points. And that indeed is less than or equal to the sum over all possible A, which in turn is the probability of the whole sample space, P of S, or 1. Second property is that the probability of the complement of an event is 1 minus the probability of the event. Since the probability of the sample space is 1, and the empty set is the complement of the sample space, then this property implies that the probability of the empty set is 1 minus the probability of the sample space, which is 1 minus 1, which is equal to 0 in this case. We can prove this result by decomposing the probability of the sample space into two sums. So the probability of the sample space is the sum over all A, P of A. We can decompose that into two parts, the points which are in the event A and the points which are in A complement. And you'll notice that this, on the left-hand side, we have the probability of the whole space, which is 1. And the first term on the right side is P of A. The second term on the right side is P of A complement. So rearranging that identity, we obtain the probability of A complement is 1 minus the probability of A. Number 3, the probability of a subset of an event. Suppose we have two events, A is a subset of B. Then the probability of A is less than or equal to the probability of B. This again is easy to show because the probability of A is the sum of the probabilities of points in A, which in turn is less than or equal to the sum over a larger sum, which includes points, all points in B, the latter being P of B. Property 4. The probability of the union of mutually exclusive events. Suppose I have two events which are mutually exclusive and therefore cannot occur on the same trial of an experiment. We're interested in the probability that A occurs or B occurs, probability of A or B. This is the probability of A union B. And it turns out that's identical to the probability of A plus the probability of B. This again is easy to show because the probability of the union is the sum of the probabilities of points in either A or B. And that can be decomposed into two classes, those which are in A and those which are in B. What is critical in this result is the assumption that the two events are mutually exclusive. Probabilities behave like areas, and certainly the area of the union of A and B is the sum of the two areas, provided there is no overlap, provided that they're mutually exclusive. 5. This is simply an extension of the property 4. It's the probability of the union of a number of mutually exclusive events. Suppose I have n mutually exclusive events such that no two of them overlap, such that for every pair of events AI intersect AJ is the empty set when I is not equal to J. Then the probability of A1 or A2 or A3 up to AN is the sum of the probabilities of the individual events. Property 6. The probability of a union of two events in general that may not be mutually exclusive can be obtained by adding together their probabilities and subtracting off the probability of the intersection. P of A or B is P of A plus P of B minus P of A and B. This is clear if I, once again, use the analogy between probabilities and areas. Suppose I add together the area of the set A and this set B. In other words, I compute P of A plus P of B. I do end up with the points in the union, all points in the union, for example, here or here. But those points that are in the intersection, they get counted twice. These once, these once, these twice. Which means that this is the probability of the union plus the probability of the intersection. And once again, by rearranging that identity, we end up with the identity in 6. Property 7 is similar to 6, only for 3 events. Let me just argue by means of, once again, drawing a picture with 3 events which may intersect A, B, and C. And suppose once again I add together the probability of A plus the probability of B plus the probability of C. Points which are here, or here, or here, they appear once in that sum. Points which are in the intersection of exactly 2 of the events, they appear twice. Points that appear in the intersection of all 3 appear 3 times. So if I were to restrict myself to P of A plus P of B plus P of C, I would like to remove the overcounting, and I begin by removing the overcounting of those points in intersections between A and B. So for example, that's these points, and those in A and C, and those in B of C. And I subtract each one of those once. And that reduces those 2's to a 1. Unfortunately, the points which are in the intersection of all 3 events, they get subtracted 3 times. Whereas I overcounted them 3 times, I've now reduced that 3 to 0. And so we add the probability of that event back in. This is called the inclusion-exclusion principle. We compute the probability of a union of events by first adding together their probabilities, and then subtracting off the probability of intersections of pairs, and then finally adding together the probability of the intersection of all 3.
Example. In a roll of 2 dice, what's the probability that the total on the 2 dice is at most 6? Let's start by defining the event A sub x, the event that the first die gives the number x, and B sub x is the event that the second die provides a value less than or equal to 6 minus x. Notice that in this case the sum will be less than or equal to 6. By independence, the probability of ax and bx is the probability of A sub x times the probability of B sub x, and the probability of ax is the probability of any one number on the first die, that's 1 over 6. Probability of B sub x, that the second die is less than or equal to 6 minus x, well, there's 6 minus x available numbers out of 6, so it's 6 minus x divided by 6. So the probability that the total is less than or equal to 6 is the probability of A1 and B1, plus the probability of A2 and B2, up to A5 and B5. Those are all mutually exclusive events, AI intersect BI, for I going from 1 up to 5. And so we add their probabilities. We've already determined that the probability of AX and BX is 1 over 6 times 6 minus x. So we add those quantities as x runs from 1 up to 5, and we get the value 5 over 12. Part B, what's the probability that the total on the 2 dice is even? Here we'll let A be the event that the first die is even, and B is the event that the second die is even. Both of these events have probabilities 1/2. Then the probability that the total is even is the probability of A and B, because they can both be even, or they can both be odd, plus the probability of A complement intersect B complement, which is by independence P of A times P of B plus P of A complement times P of B complement. That's 1/2 times 1/2 plus 1/2 times 1/2, 2/4 or 1/2. For part C, in a roll of 2 dice, what's the probability that the total on the 2 dice is divisible by 3? We break that event into the 4 possibilities. The total is either 3, 6, 9, or 12. Again, those are mutually exclusive events, so the probability we're looking for is the sum of P of A3 plus P of A6 plus P of A9 plus P of A12, where A sub x is the event that the total equals x. And all we do now is evaluate those individual probabilities. 2 out of 36 plus 5 over 36 plus 4 over 36 plus 1 over 36. Add them together and we get 1/3. Example. Strombo revisited. The letters of the name Strombolopolis are arranged at random to form another name or word. Find the probability that either the name starts with an S or that the O's all appear together. Solution. Let A be the event that the name starts with an S, and B the event that the O's occur together. The probability of A is 2 over 17, since there are 2 S's and 17 letters altogether that could appear in the first place. The probability of the event B we obtain in the numerator by pretending that the 5 O's are a single symbol, which means in the numerator there are 13 symbols in total, including the 5 O's, oo, say, but they're duplicates of the other letters, for example, S and U. So the total number of permutations such that the O's occur together is 13 factorial divided by 2 factorial times 2 factorial times 3 factorial. That forms the numerator of P of B. For the denominator, we look at the number of permutations without the restriction that the O's appear together, and this is 17 factorial divided by 2 factorial, 2 factorial, 3 factorial times 5 factorial. And this reduces to 13 factorial times 5 factorial over 17 factorial. For the probability of the event A intersect B, that the name starts with an S and the B's occur together, the probability that the name starts with an S is 2 over 17. The probability that the O's occur together somewhere among the remaining 16 places. This is a calculation exactly the same as the one we just conducted, with 17 locations replaced by 16. So it becomes 12 factorial times 5 factorial over 16 factorial. The probability of A intersect B is 2 over 17 times 12 factorial times 5 factorial over 16 factorial. But we're interested in the probability of A or B, A union B, which is the probability of A plus the probability of B minus the probability of the intersection A intersect B, or 2 over 17 plus 13 factorial times 5 factorial over 17 factorial minus 2 over 17 times 12 factorial, 5 factorial divided by 16 factorial, somewhere around 0.1194.